And the last video we are discussed about different types of interrupt and related vector address. And now coming to the instruction related to interrupt, we have mainly four instructions: EA, DA, SIM, and RIM. EA means enable interrupts, DA means disable interrupt, SIM means set interrupt mask, and RIM means read interrupt mask. Starting with EA and DA. EA and DA are the one byte instruction. When we write EA and DA of the EA and DA in the main program, this will goes to input of the flip-flop which are used for disabling and enabling the interrupt. If DA interrupt is executed unless EA is written in the program, the interrupt will not be any interrupt will not be recognized. Generally, DA is the first instruction of ISR, so that there will not be any interrupt coming to the microprocessor during that interrupt service routine is occur. So whenever we goes to the subroutine, that is ISR, we will disable all interrupt by DA instruction. Whenever we come out of from the subroutine, we will enable the interrupt by using EA instruction, so that all the disabled interrupts are again enabled by EA. So EA is the second last instruction in the ISR, and the last instruction of the ISR is always RET, that is return. And now coming to the SIM interrupt mask, it is an instruction, and there is maybe 7 bits corresponding to it. We can mask the all interrupt by using the D3 bit MSC. If it is 1, we can mask all interrupt all interrupt. If it is 0, we can disable it. And each interrupt corresponding to it, RST 5.5 has M 5.5 bit, and RST 6.5 is M 6.5, and RST 7.5 has M 7.5. If it is 0, it means it is a disabled interrupt, and if it is 1, it is a maskable interrupt. And the default bit is there, it is only for RST 7.5. We can reset the RST 7.5 using this bit. It is only for reset RST 7.5 interrupts. And others are D6 and D7, which is used for serial communication. And the RIM instruction is also there. That is read interrupt mask. We can read the status of each interrupt at a time. In the case of M5.5, M6.5, M7.5 are, we can read the maskable interrupt. If it is 1, it means that it is a maskable one, and if it is 0, it is a unmasked one. And corresponding to IE, when we write EA instruction in the our main program, it makes IE become 1. That is enable all the interrupt. If we write a DA instruction in our program, that means the IE become 0. And others are pending interrupt, that is RST 7.5 related to P 7.5, and P 6.5 related to RST 6.5, and P 5.5 is related to RST 5.5. These are the pending interrupts. And if any interrupt service is going on, at that time, any one of the interrupt is occurred here, and it will become a pending interrupt, and it will be 1 at that point. The bit corresponding to each interrupt is 1 at that time. You can read the status of interrupt at any time by using the instruction ring. After the ring instruction, the accumulator contains the each flag value. So in that accumulator value, we can take the status of each interrupt. Now again coming to the ISR. ISR means interrupt service routine. Service all the interrupts. It's a small program written in vector address related to each interrupt. In the case of ISR, when an interrupt is coming, the main program, that is microprocessor currently running main program, stops the microprocessor and jump into the ISR, that is interrupt related to the vector address. And after completing that ISR, and the last instruction to be returned, and then goes to the main program. And next session is how interrupts work. In the case of hardware interrupt, the microprocessor check for any interrupt signal. If any interrupt signal is received, at that time, microprocessor jump into the vectored interrupt location where the ISR is returned and returns to main program after completing the ISR. And in the case of software interrupt, the microprocessor has mainly 8 interrupts, that is RST0 to RST7, and it jumps to the corresponding vector location and returns to main program, completing that ISR. And the recap is we have mainly 5 interrupts. Each have edge trigger. That is RST7.5 is an edge triggered one, RST6.5 is a level triggered, and RST5.5 is a level triggered one, and trap is a edge triggered one. Trap has highest priority. Whenever a trap occurs, it is directly goes to the vector address corresponding to the interrupt. And in the case of RST7.5, that RST7.5 is stored into a D flip flop, and it is cleared by using the reset bit, that reset bit in the SIM instruction. It is also cleared by if any RST7.5 interrupt is recognized. At that time, clear will become high. And this is given to an AND gate, and that AND gate has controlled by another bit, that is M7.5. Each bit has its own bit, which is in the same instruction, which is used for masking each bit. You can disable the or enable the interrupt by using the M7.5 or 6.5, M5.5, etc. And this interrupt is also controlled by an SR flip-flop. That is, while writing EA instruction in our program, we enable all interrupt by using that SR pin. And if we use that disable pin, it is reset the SR latch. And the reset pin occur if any one of the instruction, that is DA, reset, or any interrupt is recognized, at that time reset is occurred and it will disable all the interrupt. And if the AND gate is 1, then only it goes to the corresponding vectored address related to it. And INTR, it doesn't have any vector address, is related to RST code. And if any interrupt is coming to INTR pin, the RST code will directly corresponding the vector address. And all software interrupt has its own vector interrupt, and it is routed to its own vectored address. These are all about interrupt.